Air warfare has always been misunderstood. To most people, it looks like a contest of speed and firepower: who flies faster, who shoots harder, who turns tighter. But that picture is wrong. In real combat, speed only matters after one thing is decided: position. And position, in the skies of Europe, was dictated by altitude. Altitude was not a bonus. It was control. An aircraft above its opponent could choose when to attack, how to attack, and when to leave. Gravity turned height into speed, speed into energy, and energy into survival. An aircraft below had none of those options. It reacted, it defended, and more often than not, it died. This is why the opening minutes of every air engagement mattered more than the fighting itself. Before guns fired, before formations met, before pilots even saw one another, the battle was already being shaped by the climb. The race upward determined who entered the fight with advantage and who entered already behind. In the summer of 1940, this reality became impossible to ignore. Radar stations gave warnings, pilots scrambled, engines roared. Fighters lifted off at full power and pointed their noses toward the clouds. And again, the same outcome followed. By the time defensive fighters reached combat altitude, enemy aircraft were already there, higher, faster, and ready. This was not a failure of courage. Pilots pushed their machines to the limit. Engines were run hot. Climb profiles were flown perfectly. Nothing was held back. Yet the clock kept betraying them. 2 or 3 minutes lost in the climb meant bombers crossed the coast unchallenged. Escorts arrived above the fight instead of into it. The window to intercept closed before it ever fully opened. On paper, this made no sense. Aircraft specifications showed comparable engines. Weight differences were marginal. Aerodynamics were competitive. Training standards were high. Commanders searched for explanations that fit familiar patterns. They blamed tactics. They blamed formations. They blamed pilot discipline, anything except the machines themselves. But the reports refused to change. Pilots described engines that felt strong at takeoff, then weak as altitude increased. Power that should have been available simply wasn't. Aircraft that looked equal at sea level behaved very differently: 10,000, 15,000, 20,000 feet higher. The climb slowed. Temperatures rose. Performance collapsed precisely when it mattered most. The uncomfortable truth was this: engines were producing power, but aircraft were failing to use it efficiently. Between the engine and the sky sat a component that almost no one wanted to talk about: the propeller. For decades, propellers were treated as simple devices. They spun. They pulled air backward. As long as they turned, they were considered functional. Engineering attention focused on engines, airframes, weapons, and fuel. The propeller was assumed to be a solved problem. That assumption was deadly. A propeller does not experience the same conditions throughout a flight. Near the ground, air is thick and heavy. At altitude, it thins dramatically. The angle at which a propeller blade bites the air determines how effectively engine power is converted into thrust. Lock that angle in place, and efficiency is sacrificed everywhere except one narrow condition. That was the compromise most aircraft accepted. Fixed-pitch propellers forced pilots to choose their weakness before leaving the ground, optimize for takeoff and climb, and sacrifice speed and efficiency later. Optimize for cruise, and accept long, painful climbs. Either way, the aircraft was operating outside its ideal performance envelope for most of the mission. In combat, this compromise became lethal. Every second spent climbing inefficiently widened the gap between attackers and defenders. Enemy fighters reached altitude first and waited. They attacked from above, disengaged upward, and returned with gravity on their side. Defenders arrived late and tired, their engines already stressed, their options already limited. The war was not being lost because aircraft were inferior. It was being lost because power was being wasted. And the most disturbing part was this: engineers had known this for years. The data existed. Wind tunnel tests existed. Flight trials existed. Solutions had been proposed, tested, and proven in controlled environments. But they challenged a belief that ran deep in military aviation culture, that simplicity was safety, and complexity was danger. Anything that adjusted automatically was viewed as untrustworthy. Anything hydraulic was viewed as fragile. Anything that removed control from the pilot was assumed to fail at the worst possible moment. So, the simplest option was chosen, not because it was best, but because it felt safe. That belief shaped doctrine. It shaped procurement. It shaped training. And it shaped the early air war over Europe. By the time combat exposed the flaw, the consequences were already unfolding. Aircraft were arriving late. Bombers were slipping through. Pilots were dying not because they lacked skill, but because the climb had already decided the fight before they ever saw the enemy. This was the paradox at the heart of the air war. The machines were powerful enough to win, but restrained by a choice made long before the first shot was fired. And once that realization took hold, a more dangerous question followed. If the problem was not the pilots, not the aircraft, but a single overlooked detail, how much more time could be lost before someone dared to change it? You could feel the pressure building, the clock was already running, and gravity was still on the enemy's side. Air combat is not decided by who flies faster at top speed. It is decided by who arrives first, who reaches altitude first, who enters the fight with energy, position, and choice. In the skies of early World War II, altitude was not an advantage, it was survival. Fighters that climbed faster chose when to attack. Fighters that climbed slower were forced to react, usually too late. This is where the problem began. Most air forces entered the war believing they already understood the limits of their aircraft. Engines were powerful. Airframes were refined. Pilots were trained. On paper, everything looked balanced. Yet in real combat, pilots kept reporting the same frustration. Enemy aircraft were already above them, already diving, already gone before a counterattack could even begin. The instinctive explanation was always the same. Better pilots, better tactics, better engines. But none of those answers held up under scrutiny. Time after time, investigations showed that opposing fighters often used engines of similar power, aircraft of similar weight, and pilots with comparable training hours. The difference appeared somewhere else in the climb phase, the most neglected and least glamorous part of air combat. Climb performance depends on how efficiently an aircraft converts engine power into thrust across changing conditions. Near the ground, air is dense. At altitude, it thins rapidly. Engines behave differently. Propellers behave differently. And yet, most aircraft relied on a solution that treated all altitudes as if they were the same. Fixed-pitch propellers were simple. Their blades were locked at a single angle, optimized for one condition only. Set them for takeoff, and the aircraft climbed reasonably well, but lost speed at altitude. Set them for cruising speed, and takeoff and climb suffered badly. Pilots had to choose before they even left the runway which weakness they were willing to accept. Military planners accepted this compromise because it felt safe. Simple meant reliable. Fewer moving parts meant fewer failures. In combat aviation, complexity was treated as an enemy equal to the opposing air force. Anything automatic was viewed with suspicion. Anything hydraulic was viewed as fragile. Anything that adjusted itself without pilot input was assumed to fail at the worst possible moment. This mindset created a quiet but deadly illusion. Engineers optimized engines, airframes, and weapons, while ignoring the one component responsible for translating all that power into motion. The propeller was treated as an accessory, not a decisive system. It was assumed that as long as it turned, it worked. But in combat, working was not enough. A fighter that climbed 2 minutes slower did not just arrive late, it arrived already defeated. By the time it reached altitude, enemy fighters had already chosen their targets, attacked from above, and escaped using gravity itself as a weapon. No amount of pilot skill could compensate for physics. From early air battles painted a disturbing picture. Pilots described pushing engines to their limits during climbs, watching temperatures rise, power fall off, and performance collapse as altitude increased. Engines were capable of more, but propellers could not adapt. They forced engines to operate outside their optimal range, wasting power when it was needed most. This wasn't a mystery. Engineers had understood the theory for years. An engine produces power efficiently within a narrow band of revolutions. A propeller, however, experiences radically different aerodynamic loads at different air densities and speeds. Locking blade angle meant locking inefficiency into the system. The aircraft carried power it could not fully use. Yet the industry resisted change. The moment variable systems were proposed, objections flooded in. Too heavy, too complicated, too many failure points. Too dangerous for combat aircraft that would be damaged, frozen, shaken, and abused. Manuals warned that a jammed mechanism could be fatal. Training officers worried pilots would be distracted. Procurement officials worried about maintenance. So air forces accepted the delay. They trained around it. They built tactics around climbing slower. They told pilots to adapt, and pilots paid the price. What made the situation truly tragic was that the delay was invisible on blueprints. On design tables, aircraft looked equal. In flight tests that focused on level speed, numbers looked competitive. Only when time and altitude were measured together did the truth emerge, and by then, battles were already being lost. Every scramble began with a race against gravity. Radar warnings arrived. Pilots ran to aircraft. Engines roared to life. And then came the climb, the longest, most vulnerable phase of the mission. Fighters clawed upward while enemy formations continued forward unchallenged. By the time interception altitude was reached, bombers had already crossed defensive lines, and escorts were already positioned above. The war was exposing a flaw not in courage or skill, but in assumptions. The belief that simplicity guaranteed safety was quietly killing pilots. The belief that one mechanical choice could not outweigh training and tactics was proving false. And the most dangerous realization of all was this: the solution did not require new aircraft, new engines, or new pilots. It required admitting that the simplest answer had been wrong, but admitting that would mean rewriting doctrine, retraining crews, retooling factories, and accepting complexity in the one place militaries feared at most, the heart of their machines. Time was already short, enemy aircraft were already improving, and every minute lost in the climb was another minute handed to the enemy. The question was no longer whether air forces could afford to change. It was whether they could afford not to. The idea itself wasn't radical. That was the cruel irony. It didn't require new physics, exotic materials, or untested engines. It required admitting something deeply uncomfortable: that the propeller, long treated as a passive component, was in fact an active system, one that needed to think faster than the pilot. The concept was simple to describe and terrifying to approve. Instead of locking the propeller blades at a single angle, allow them to change their pitch automatically while spinning. Let the blades flatten during takeoff and climb, allowing the engine to spin freely and produce maximum power. Then, as speed and altitude increased, let those same blades rotate to a steeper angle, converting that power into efficient forward motion rather than wasted revolutions. On paper, the math was flawless. Engines operate best within a narrow range of revolutions per minute. Fixed-pitch propellers forced engines outside that range during most of a flight. A self-adjusting propeller would keep the engine exactly where it wanted to be, regardless of altitude, speed, or maneuver. Maximum thrust when climbing, maximum efficiency when cruising, automatic protection against overspeed during dives. It was, in every measurable way, superior. And that was precisely the problem. Military aviation culture did not reward elegance. It rewarded predictability. Pilots trusted cables, levers, and systems they could feel. Engineers trusted simplicity because simplicity could be inspected, repaired, and explained. An automatic system that adjusted itself in mid-air, using oil pressure and centrifugal force, felt like surrendering control at the exact moment control mattered most. The objections were immediate and relentless. What happens when the system fails at altitude? What happens when oil thickens in the cold? What happens when shrapnel damages a line? What happens when a mechanism jams and locks the blades in the wrong position? In combat, pilots didn't want explanations, they wanted certainty. The irony was that fixed-pitch systems failed quietly all the time. They failed by wasting power. They failed by overheating engines. They failed by forcing pilots to fight physics instead of the enemy. But those failures were invisible. They didn't look like breakdowns. They looked like bad luck. Automatic systems, by contrast, made everyone nervous because when they failed obviously. This fear hardened into doctrine. Reports were written, committees convened, warnings circulated. The prevailing judgment was clear. The gains were real, but the risks were unacceptable. Performance meant nothing if reliability could not be guaranteed under combat conditions. And combat conditions were unforgiving beyond anything peacetime testing could simulate. So the idea stalled. Factories continued producing aircraft optimized around compromise. Pilots continued training to manage engines manually, juggling throttle, mixture, and propeller controls, while flying, navigating, communicating, and fighting. Every climb remained a race against time, and gravity kept winning. But reality has a way of ignoring doctrine. When aircraft equipped with automatic pitch control finally flew alongside their fixed-pitch counterparts, the difference was not subtle. It was immediate. Takeoff distances shrank. Climb rates surged. Engines ran cooler and smoother. Pilots reported something almost heretical in wartime aviation: reduced workload, fewer controls to manage, fewer decisions to make under stress. Instead of fighting their machines, pilots could focus on the fight. Still, resistance remained. Performance tests could be dismissed. Demonstrations could be explained away. Critics argued that short trials meant nothing compared to months of combat abuse. They warned that complexity always reveals its price, eventually, usually in blood. And then came the moment no one could ignore. 2 aircraft, same engine, same airframe, same fuel load, same pilot. One difference. One climbed as expected, slowly, steadily, predictably limited. The other climbed like something unshackled. It reached altitude minutes earlier. It retained power where the other gasped. It did not demand constant attention. It simply worked. This was not a marginal improvement. It was a structural advantage. The conclusion was unavoidable and deeply unsettling. Air forces had not been losing altitude because their aircraft were weak. They had been losing because their assumptions were wrong. The technology they feared was not fragile. Their trust in simplicity was. Accepting that truth meant crossing a line. It meant acknowledging that the safest system was not the simplest one, but the one that adapted faster than the battlefield itself. It meant redesigning training, maintenance, logistics, and doctrine not next year, but now. War does not wait for consensus. It punishes hesitation. And while committees debated and factories hesitated, the enemy continued climbing faster, higher, and with deadly patience. The question was no longer whether the idea worked. The question was whether there was still time to deploy it before the cost of delay became irreversible. The most dangerous moment in any war is not when a new weapon appears, but when a solution exists and is ignored. By the time air forces began to understand what automatic pitch control truly meant, the war was already moving faster than their institutions could react. The technology was no longer theoretical. It had flown. It had climbed. It had proven, repeatedly, that aircraft equipped with adaptive propellers reached altitude sooner, retained power longer, and gave pilots an advantage that could not be trained into existence. And yet, adoption moved at the speed of paperwork. Military aviation was built on procedure. Every change required approval, testing, retraining, and production adjustments. In peacetime, this caution saved lives. Wartime, it nearly cost nations their survival. Commanders worried about maintenance complexity. Procurement officers worried about supply chains. Training departments worried about pilots relying too much on automation. Each concern was reasonable in isolation. Together, they created paralysis. Nowhere was this delay more dangerous than in Britain. British fighters were not inferior by design. Their airframes were agile. Their engines were powerful. Their pilots were experienced and determined. But their aircraft climbed too slowly. Again and again, pilots reported the same problem. Enemy fighters reached altitude first, attacked from above, and disengaged at will. The skies were not being lost because of courage or skill. They were being lost because physics favored the side that adapted faster. What made the situation almost unbearable was that the solution was within reach. Automatic propeller systems were already being produced elsewhere. Licenses existed. Designs were known, but institutional resistance moved slower than the enemy. Every intercepted bomber that slipped through defenses reinforced the cost of delay. Every failed interception made the math clearer. Minutes lost in the climb translated directly into bombs falling unopposed. Radar warnings were useless if fighters could not reach intercept altitude in time. Defensive systems were only as fast as the slowest component in the chain. Pilots felt this gap most acutely. In the cockpit, they did not think in terms of doctrine or logistics. They thought in seconds and meters. They knew when an enemy aircraft was above them, they were already at a disadvantage. They knew when an engine struggled during climb, no amount of bravery could compensate. They were living inside a flaw that planners still debated on paper. The turning point did not come from a committee. It came from desperation. Faced with the reality that existing tactics could not close the gap, frontline units began pushing for immediate changes. Normal approval channels were bypassed. Emergency authorizations were granted. Aircraft were modified not because doctrine allowed it, but because survival demanded it. The risk of complexity suddenly seemed smaller than the certainty of defeat. When the first fighters equipped with automatic pitch control entered service, the effect was immediate and unmistakable. Scramble times shrank. Climb performance improved across every altitude band. Pilots reported reaching combat zones earlier and with energy to spare. For the first time, they were not chasing the fight, they were arriving ahead of it. This shift changed everything. Interceptions that once failed now succeeded. Bombers that once slipped through now faced opposition at altitude. Escorts that once dominated now had to fight for position. The air war did not change overnight, but the balance tilted just enough to matter. And that was the cruel lesson. The difference between holding the line and losing it was not a revolutionary aircraft or a miracle engine. It was the willingness to accept complexity in time. Delay had almost turned a solvable problem into an irreversible one. By the time widespread adoption began, the margin was razor thin. Had the change come months later, the outcome might have been different. Not because the pilots were weaker, not because the aircraft were worse, but because hesitation had allowed a known advantage to remain unused while the enemy pressed forward. War does not forgive timing errors. It punishes them without mercy. And as air forces rushed to retrofit, retrain, and reorganize, one unsettling question lingered beneath every successful interception. If this solution had been accepted earlier, how much blood could have been spared? Accepting the solution did not end the problem. In many ways, it created a more dangerous one. Once automatic pitch control became standard, aircraft performance surged across the board. Fighters climbed faster, cruised farther, and fought with energy advantages that reshaped air combat. Bombers gained altitude margins that placed them beyond the reach of older interceptors. On paper, the technology had delivered everything it promised. Reality, however, demanded payment. Scaling a complex system from limited trials to mass wartime production exposed weaknesses that no test range could fully reveal. Propeller was no longer a simple assembly of blades and hubs. It was a precision machine, dozens of components, tight tolerances, hydraulic pathways, governors that had to respond flawlessly under vibration, cold, heat, and combat damage. What worked perfectly in controlled testing now had to work thousands of times, in thousands of aircraft, flown by thousands of crews, under conditions no engineer could predict. Factories expanded overnight. Skilled craftsmen were replaced by rushed training programs. Production lines ran around the clock. Quality control fought a losing battle against speed. And, inevitably, failures appeared. At first, they were small. A sluggish response here, a pressure fluctuation there. But in combat, small mechanical flaws do not remain small. They compound. A delayed blade adjustment during climb, a governor that hesitated under extreme cold, a hydraulic line contaminated during hurried maintenance. Each defect carried consequences measured not in inconvenience, but in lives. The most dangerous failures were not dramatic explosions or obvious breakdowns. They were subtle. A propeller that failed to hold its feathered position after an engine loss. A system that slowly drifted out of optimal settings while crews believed it was protecting them. These failures betrayed trust, and in wartime aviation, trust is as vital as fuel. Crews began to talk. Stories circulated of aircraft that should have made it home but didn't. of bombers that lost altitude instead of stabilizing, of fighters that climbed brilliantly one day and struggled the next. Skeptics seized on every incident as proof that complexity had finally shown its true cost. This was the moment when many technologies died in past wars. It was easier to blame the system than to fix it. Easier to retreat to simplicity than to confront industrial shortcomings. Easier to argue that pilots should adapt rather than machines improve. But this time, retreat was no longer an option. Too much depended on the advantage the system provided. Removing it would mean surrendering altitude, speed, and survivability advantages the enemy would not give back. So the response changed. Instead of denying failure, engineers confronted it directly. They studied crash reports not to assign blame, but to extract data. They examined recovered components under microscopes. They replicated battlefield conditions in test facilities that pushed systems far beyond design limits. Cold, colder than any altitude. Vibration harsher than any engine could produce. Contamination worse than any maintenance error. This was adaptation under fire. Designs were revised, redundancies added, tolerances tightened, manufacturing processes rewritten. Quality control slowed production but saved aircraft. Pilots were retrained not just to fly the system, but to understand its behavior when damaged. Maintenance crews learned to treat the propeller not as an accessory, but as a critical life support system. Gradually, failure rates dropped. What emerged was not just a working technology, but a hardened one refined by combat, corrected by loss, and validated by survival. The same complexity once feared now delivered reliability unmatched by simpler systems. Automatic adjustment reduced mechanical stress. Engines ran smoother. Structural failures decreased. The system proved more forgiving under damage than anyone had predicted, and the battlefield noticed. Aircraft returned home on fewer engines. Fighters escaped dives that would have destroyed them before. Bombers limped back across hostile skies because drag disappeared when it mattered most. The technology did not eliminate loss, but it shifted probabilities, and in war, probability is destiny. By the time the balance stabilized, one truth had become impossible to ignore. The cost of adaptation was real, but the cost of refusing it would have been catastrophic. Complexity had demanded discipline, honesty, and relentless correction. Simplicity had demanded only faith, and faith had failed. The advantage that once seemed risky was now indispensable, not because it was perfect, but because it evolved faster than the war itself. And in that evolution lay the quiet answer to a question few dared to ask at the beginning. Survival does not belong to the strongest or the bravest, but to those willing to change before hesitation becomes fatal. Final years of the war, the argument was over. Not in meeting rooms, not in technical papers, but in statistics written in wreckage and survival reports. Aircraft equipped with adaptive propeller systems were no longer an experiment. They were the standard. And their impact was no longer theoretical, it was measurable. Fighters climbed faster into combat zones. Bombers operated higher than enemy interceptors could reliably reach. Crews returned home on damaged aircraft that would once have been lost without question. What had begun as a disputed engineering idea had become a margin small on paper, decisive in reality. War is rarely decided by a single breakthrough. It is decided by accumulated advantages. A few minutes saved in a climb, a few thousand feet gained before engagement, a few percent improvement in fuel efficiency that extends patrol time. None of these win battles alone. Together, they decide outcomes. This was the true power of the technology. It did not make aircraft invincible. It made them forgiving. It turned errors into survivable events. It gave pilots choices where once they had none. In air combat, choice is everything. Enemy pilots noticed first. Reports described Allied aircraft that seemed to appear above engagements without warning. Fighters that could disengage upward instead of diving away. Bombers that maintained formation despite losing engines. The sky itself no longer behaved the way opponents expected. Behind these effects was no secret weapon, no radical airframe, no new engine class. It was the same machines, finally allowed to use their power efficiently across the entire fight. By the war's end, analysis revealed what combat crews already knew. Aircraft losses dropped not because missions became safer, but because survivability increased. Engines ran closer to optimal limits. Structural stress decreased. Emergency situations that once guaranteed destruction now had margins for recovery. The difference between loss and return was often invisible, a blade angle, changing at the right moment, without a pilot ever touching a control. The greatest irony was this. The system once feared as too complex had become more reliable than the simplicity it replaced. Automation did not weaken pilots. It freed them. It removed mechanical burdens so human judgment could focus where it mattered: tactics, awareness, survival. And yet, the final lesson had nothing to do with propellers. The real story was about timing. The solution existed years before it was accepted. It was rejected not because it failed, but because it challenged beliefs. It demanded trust in data over intuition, adaptation over tradition, change over comfort. When those beliefs finally broke, the cost of delay was already written in lives. History often frames victory as inevitable. It was not. It rested on margins so small they were almost ignored until they were not. A detail smaller than a cockpit did not win the war by itself, but it shifted the balance just enough, soon enough, to matter. And that is how wars are truly decided, not by grand moments, but by the willingness to change before the margin disappears. You could build the best aircraft in the world, train the bravest pilots, design the perfect strategy, and still lose if you refuse to adapt when the evidence demands it. That is the question this story leaves behind. Not how powerful a nation can become, but how quickly it is willing to admit it was wrong.